Hello and welcome to Some Assembly Required. David Murray, aka the 8-Bit Guy, kinda recently released video number 8 in his History of Commodore series, this time about the Amiga 1000. This video is about urging you to go see that video, if you haven't already. This video touches a few sentimental points for me and I wanted to share. Growing up, my first couple of computers were Apple II computers. First a Taiwanese compatible Apple II Plus, much like this one, and then a Taiwanese compatible Apple IIe. I played games on this computer, I programmed those computers both in BASIC and in assembly. I loved those computers. But I couldn't help but feel a little envious of other computers. During the 80s, what computers were around you was pretty much a matter of geography. In Israel, where I grew up, the common 8-bit computers, aside from the Apple II, were the ZX Spectrum and the Commodore series. When comparing the games I was playing to the games available on my friends' computers, I couldn't help but get a feeling of inferiority. Even the Spectrum, which was inferior to the Apple on many fronts, had games that were much more colorful. And you can tell I was not alone. If you go to the Apple II subreddit, you will notice that the upvote button is shaped like the 80s Apple logo, whereas the downvote button is shaped like the Commodore logo. That feeling of rivalry was not something unique to me personally. And then I saw the Amiga 1000 at a friend's house, and I was blown away. It was not just another computer. It was something completely different. Eventually I got an Amiga 500, and while I of course played games on it, I also programmed it both in C and in assembly. I learned about how it works and what hardware it had. I spent hours reciting the Amiga's superiority to anyone who would listen, and quite a few who wouldn't. And that's what I love about 8-Bit Guy's video. Whenever I see people talking about the Amiga, I always feel they miss the point. I don't know whether it's through owning the machine for a year or whether it was the research he did for that video, but he managed to hit all the important points of what made the Amiga such a great computer to own and to program for. Not only did it have groundbreaking hardware capabilities, but it also had an OS at least one level above the best any other home computer operating system could offer at the time. Only a decade later, in 1995, did PC operating systems started to offer a comparable level of OS services as what the Amiga could do in 1985. On the hardware side, PCs took even longer to close the gap. 16-bit colors only started to be available towards the end of the 20th century, hardware graphics assists took about as long, and programmable hardware assists took even longer. In the 80s, as I was lecturing unsuspecting people on the virtues of the Amiga, a subject matter they cared not about, what the message I was actually trying to get across was, can't you see how far ahead of its time this computer is? And that is precisely David's message on the Amiga, which is why you should absolutely go and see his video. Having said that, you just cannot do a video about the subject matter I both know and care so much about without me having some nits to pick. So here goes what I liked less about 8-Bit Guy's video. The first is not something David did or say, but something he didn't do. He didn't show you a specific demo. He didn't show you Boing. You might be wondering what's so special about this demo. I mean, compared to some demos that ran on the same hardware, Boing is downright bland. However, Boing is a very important demo, arguably the most important demo, for two reasons. First, this is the demo that introduced the computer. At CES in 1984, before Commodore acquired the company, the computer was shown running this demo. In fact, that's all it could do, as it had no operating system at the time. The computer was implemented using breadboards, and some of the chips kept frying. And yet, it blew people's mind away. People kept searching for the real computer driving this demo, not believing that what they were seeing was it. Since this demo does in fact look lame today, allow me to tell you what I found so amazing about it. I first saw this demo the first time I saw an Amiga at a friend's house. And yes, it totally blew my mind away. Try watching this with 8-bit computers user's view. What we have here is a huge object moving and rotating at a smooth 60 frames per second while casting a shadow that isn't black. And then there's the sound. Aside from the wonderful boing sound, the sound itself goes left and right as the ball moves left and right. Compared to 80s computer, this is just another level. So that demo was really instrumental to the computer, enough so that when Commodore finally gave up the ghost and sold the Amiga intellectual property, the red and white checkered ball actually became the official logo. I will note that there were numerous references to it even before then. Boing never really went very far. To be fair to David, he did mention this demo in a later video, the one about the A500 Mini. The second nit I have to pick is about this part of the video.
The CPU was the Motorola 68000, a 16-bit CPU with even some 32-bit internal registers. It runs at 7.16 MHz. Now you might think it would be 7 times faster than the CPU in the Commodore 64, which runs at 1 MHz, but that's not actually the case. The 6502 and its variants are very efficient and perform a lot more operations per clock cycle than the 68000. In fact, if both CPUs were clocked at 1 MHz, the 6502 would achieve 0.43 MIPS, whereas the 68000 would only achieve 0.175 MIPS. But since the 68000 is clocked 7 times faster, it ends up being 1.25 MIPS, which means it's about 2.9 times faster than the C64. So yes, the CPU is more powerful, but probably not as much as people might think.
Having started building a cycle-accurate 6502 clone myself twice, I'll be the first to admit that the 6502 is very efficiently built. Each opcode takes between 2 and 7 cycles, with most running at about 3 or 4 cycles. The 68000, on the other hand, accesses the memory in what's called a bus cycle. This bus cycle takes 4 CPU cycles. This means that merely fetching the opcode from memory takes 4 cycles. It is fair to say that opcodes on the 68000 take considerably longer to run than on the 6502. So why do I consider David's statement wrong? Well, it's not wrong per se, it's just highly misleading. To understand why, let's look at the two CPU's architectures. The 6502 has one general-purpose register called accumulator. It has 2 index registers called X and Y. It also has a stack pointer and a status register and a program counter. All registers are 8-bit except program counter, which is 16. As far as memory access goes, the CPU has 16 bits addresses, or 64 kilobytes, at 8 bit per access. This is what makes it an 8-bit CPU after all. The 68000 has 16 general-purpose registers and a 32-bit program counter. Of the 16 registers, 8 can be used as either 8, 16, or 32-bit registers, while 8 can only be used as 16 or 32-bit. The former are called the data registers and are denoted D0 through D7. The latter are called address registers and are denoted A0 through A7. Almost nothing about their actual use, however, dictates this division. You will notice that I did not mention a stack pointer. That's because register A7 is used as a stack pointer. At least on the Amiga, A6 was used as a base pointer for function calls, and A5 was used for library load addresses. That still left 13 32-bit registers for doing whatever you wanted. The 68000 has 24 bits of address bus, giving it 16 megabytes of accessible memory, and 16 bit of data bus. Technically, this makes it a 16-bit CPU. With every single aspect of its internal implementation being 32-bit, however, it seems strange to call it that. The simple fact is that later versions of the Amiga and the Macintosh switched to a truly 32-bit 68020 with almost no transition costs at all. The programs already were 32-bit, and it just took the CPU family a couple of iterations to catch up. Most importantly in that regard is the fact that the registers were as wide or wider than the address bus. What this means is that, unlike the 6502, you can hold an entire memory address in a single register. This affects the addressing modes available, which are far richer and more capable on the 68000 than on the 6502. The practical upshot of all that is that, while each operation indeed took longer on the 68000, it also did more. Comparing just the number of cycles it took an operation to complete is, in my opinion, not very indicative. To showcase that point, I'm going to go into the weeds and get technical. If the analytics of this video show that people left at this point, I'll completely understand. In particular, let's actually implement an operation one might wish to perform on an actual computer. Let's take displaying a value as a decimal number. For the sake of keeping things simple, let's assume this is an 8-bit number. Let's also compare our 6502 execution to a 68000 execution at the same clock speed, just so we can compare Commodores to Commodores. I mean apples to apples. To convert a number to another base, we need to repeatedly divide by our target base, so 10 in our case. The remainder is the next unknown least significant digit, and the quotient is carried over to further division. When the quotient is 0, we're done. So let's see how many cycles we need in order to divide on the 68,000. We need 140. Yeah, that doesn't seem very efficient. Let's see how many the 6502 needs. Add and shift, decrement, exclusive subroutine, low, reset, turn from interrupt, store, transfer, wait. There is no division in 6502. If we want to divide two numbers, we need to explicitly write the code. We implement the operation manually by doing what's called long division. In essence, this is a series of shifts and subtraction. We shift the divider left until it is flush with the number we want to divide by. Since we don't know what that number is, we'll just shift it left 4 bits, which will make it flush with the byte's most significant bit. We then try to subtract the shifted divisor from the dividend. If we can, i.e. the dividend is bigger than the shifted divisor, we mark the relevant bit in the quotient as 1. If it is not, we undo it and mark the relevant bit in the quotient as 0. We then shift the divisor right by 1 bit and repeat until the shifted divisor is the same as the unshifted original divisor. At this point, what remained after all subtraction is the remainder, and we filled in all the bits of the quotient. So let's see how this code looks. We'll call the function div10. We'll need 2 memory locations, and since we want the access to be quick, we'll put them both in 0 page. So the first location will be the result. We can put that anywhere in the first 256 bytes. We'll put them right in the middle. And the second one was just somewhere we store temporary values. So let's put that one after that. We need to initialize the result to 0. So let's do store 0 at div10 result. We'll store the divisor in div10 TMP. And our divisor is 10 shifted left by 4 bits. Next, we need to set up a loop, and we need to keep track of how many times the loop is running. Here we enter the actual loop. We'll use a local label to jump to. We need to subtract the shifted divisor from the divided. Subtraction on the 6502 has to happen with the carry flag set, or it will be off by 1. If our divided number is bigger than the divisor, the carry will be set, in which case we want to shift 1 into the result. If it is not bigger, then we need to shift 0. So we can just do... There's a problem though. If the number is too small, we need to undo the subtraction. So we'll just store the value of a before the operation, and then restore it afterwards if the value is too small. Next, we need to shift the divisor. We'll decrease the loop count by 1. And if it's not done, i.e. if it's not 0, loop back. And pretty much that's it. Just return from subroutine. Div10 result will contain the quotient and the accumulator will contain the remainder. There's just one problem though. We're overwriting the values of x and y, and that's not a polite thing for a subroutine to do. So let's push them to the stack at the beginning and pull them from the stack at the end. Let's however measure how long it takes. Push x and push y take 3 cycles each. Store 0 to 0 page takes 3 cycles. That's 2 to fetch the opcode in the address in 0 page and 1 to do the actual save. Load x immediate takes 2 cycles. Store x in 0 page takes 3 cycles. Load x immediate again takes 2 cycles. And then transfer AY 2 cycles. Set carry 2 cycles. That's pretty much the minimum any 6502 operation takes. Subtract from the carry takes 3 cycles. Branch carry set takes 2 cycles if not taken and 3 cycles if it's taken. And transfer YA takes 2 cycles. So the 2 operations together take 4 cycles if the branch is not taken and 3 cycles if it is. Since there's pretty much equal chance it will or will not be taken, let's just count that as 3.5 cycles. The rotate left needs 3 cycles for the 0 page address. However, it's a read modify write command, so it needs 2 extra cycles, so 5 altogether. The same goes for the logical shift right. Decrement x 2 cycles. Branch not equal is like branch carry set. It needs 2 cycles if it's not taken and 3 if it is. However, we do know how many times it will be taken. It will be taken 4 times and not taken the 5th time. So 14. Pull Y and pull X require 4 cycles each, and return from subroutine requires 6 cycles. So just the operations inside the main loop requires 126.5 cycles. Add to that the setup and teardown of the function, and we're already at 150 cycles. We actually also need to account for the return from subroutine and the jump to subroutine. That puts us as around 160 cycles. To see that in action, let's turn this into an actual program. So we're going to need the reset vector, and we're going to need an actual program. We'll load the value to be converted to decimal into the accumulator, and we'll keep track of how many digits we have so far in the X register. Now we need to loop. We can use the same local label as before, because between those labels there is a global label, which means that the assembler treats this one and this one as different labels. That's what local label means in this context. We'll just jump to our divide subroutine. We'll store the digit we got in memory, increment X, and use the quotient as the value to divide for the next digit. We'll do that until the quotient is 0, which means that we're done. The computer will be running this runs the program until it sees a write to a certain address. So that's pretty much the program. To run the program, we'll use common components that every household has. In particular, we'll be using a 6502 controlled by an Arduino computer connected to our computer, where all the buses are controlled by the Arduino. So, like I said, everyone has one of those lying around. So just use our existing makefile in order to compile, load to the test harness, and run. So there you have it. Let's verify that this indeed did what we thought it should do. So we write 6 to 8000, and then we write 2 to 8001, and then we write 1 to 8002, and that's it. So 126, that's precisely the value we wrote there. And the whole thing took just 550 cycles. Now, to be fair, if we're really stressed for time, we can make this program run faster, but it's going to cost us. The main way we can do that is by unrolling this loop. Instead of looping over this code 5 times, we'll just duplicate it, which means we do not need the branch not equal, and we also do not need to shift right our divisor the last time. We also do not need to set anything with the X register, which means we do not have to save it and then restore it. It does mean that we will need to use Y here instead of X, but that's fine. And that should shorten our runtime by somewhat. The practical upshot of all of that is that while the 6502 can certainly be faster than the 68000 at the same clock speed, that was not always the case. You'll notice that our last version of the program, the one that did run faster, did not run faster by an order of magnitude. Even that was achieved only through very aggressive optimizations that only make sense for code that gets called a lot. And that's before mentioning the obvious. Printing only 8-bit numbers was not very useful, not even on the 6502 computers. You'd usually want to print at least 16-bit numbers. On the 68000, the DVU instruction is perfectly capable of handling 16-bit numbers. On the 6502, we simply do not have enough register storage space. We'd have to start juggling numbers back and forth with temporary storage in memory. This would mean more zero-page addresses used and more time. Another point to consider about dividing 16-bit numbers by 10 is that we would have to shift the divisor by 12 bits, not 4. This means that unrolling the loop would require repeating it 13 times. This begins to take a considerable amount of space and is even less likely to make sense. As such, we can confidently say that we can make the 6502 divide an 8-bit number by 10 faster than on the 68000, if we care enough about this particular operation speed. Dividing a 16-bit number by 10, however, will definitely take longer, possibly much longer, on the 6502 than it does on the 68000. So there you have it. Like I said, 8-Bit Guy's video is great and you should absolutely go see it. What little criticism I have can be filed away as nitpicking by an overzealous fan of the platform. The next video will likely be the last one before we start actually building 6502-based computers. At this point, the CPU is more or less completely implemented. The next video, I'll try to optimize the design so that it takes less logic gates, but frankly at about 1000 LUTs it is already small enough to be practical, at least for this phase of the project. In the meanwhile, thank you for watching and liking. I'll see you next time.